Okay, so now it's recording. So what I intend to do is to review quickly the concept of the exam, well, the major topics that the exam might include, and then go to solving one exam that covers most of the those topics. Now, the exam is mostly chapter 6 and chapter 7, 8, the part that we did, of course, and yeah, here. And I will start by Schrödinger's equation. Though, well, by the way, those are not this is not an exhaustive list of what we would do in the exam, what we get in the exam, but at least this gives you an idea about the exam. And also, I mentioned these topics in order not to forget about them. So the Schrödinger's equation, you all know, Schrödinger's equation is minus h bar squared 2m dx squared plus v psi is equal to I h bar psi t. And now I can, one of the question could be using a typical, let's say, just a one dimension equation or a wave function, which is a exponential a kx minus omega t. Using this equation, prove that or derive the operator, momentum operator, and energy operator. So this we have done in class. I will not repeat it, and it is also in the text. Okay, so this is something that, or I can ask you, okay, the momentum or the energy operator, apply it to this this wave function. So what should be what should be the result? Okay. So then let's go to the part where obviously Schrödinger's equation, we did several special cases like the infinite well potential, the finite well potential. We also did the case where you have tunneling, where the particle is going with an energy, where the energy is larger than the potential, and the case where the energy of the particle is smaller than the potential. And we have seen the reflection properties and also transmission properties or probabilities. So reflection from this side and transmission in this side. Okay, so this we have done. I will not repeat it here. And then we apply Schrödinger's equation to the hydrogen atom, and we got the quantum numbers. So the quantum numbers that n equal 1 to infinity, it's a positive integer, a non-zero positive integer. L is the angular quantum number, and it goes from L to n minus 1. And then ML is the magnetic quantum number, which goes from minus L to plus L. And then we also saw the MS, which is plus minus 1. So those are the quantum numbers, and those quantum numbers are the one that gives the identity of the electron in the atom. Okay, so, and we have seen also the exclusion principle of Pauli, that states that two electrons cannot have the four same quantum number. Okay, in the atom. So you cannot find an electron in the same atom with the four similar quantum numbers. They must differ by at least one. So this is yeah. So let's give an example. If I tell you that an atom that has 7 electrons, okay? I think it's a nitrogen. So an atom that has 7 electrons, we know that, so I might tell you, give me the electronic configuration, but explain what. So again, n equal 1, we always start from n equal 1. N equal 1, we are talking about shell number 1. Okay. Shell K, shell K, shell K, shell K, and n equal 1. And then L equals 0, and ML must be equal 0, and then MS is equal plus minus 1. Now, what is the the subshell here, okay, we know that subshell is taking the quantum principal quantum number and the letter that goes with L equals 0, with L. So when L equals 0, we call S, L equal 1, P, L equal 2, SPD, and L equal 3, F. So in this case, I have 1 S, and since I have 2 electrons, this is 1 S2. And then we go to N equal 2. So N equal 2, we know that L can be 0, but L also can be 1. So L is equal 0 means ML equals 0, and MS is equal plus minus 1/2. We can easily see that in this quantum, in this subshell, so of course here we talk about shell KL, okay? Here we are talking about shell subshell 2 because N equal 2, and subshell S because L equals 0, and there are 2 electrons that we already populated here. Okay. And then when we go to L equal 1, ML can take 3 values, plus 1, 0, and minus 1. And of course, MS can take plus 1, minus 1, plus minus half, plus 1/2, plus minus 1/2. Now, in total, you can get up to 8 electrons here. Sorry, 6 electrons in total, 6 electrons. 6 electrons, but in this specific case, where we have an atom that has 7 electrons, we already put 2 here, This means that the remaining will be 3 electrons to be put here. So the state is 2, or subshell is 2. The subshell L equal 1 correspond to a letter P. And since we are populating 7 electrons, there are 3 that are remaining. So this will be a way to explain to me the electronic configuration. So this configuration, this atom will have 1s2, 2s2, and 2p3. This is the electronic configuration of this atom. Any question? Okay. Excuse me, can you mute? So yeah, let me just pause the recording. You recording? Yeah. So this.
Professor.
Yes, please.
Yes, I just have one question. The 6 electrons at the end. Can you just explain it a bit? I didn't really follow there.
Yeah. Okay. So let me just. Yes, maybe I went very fast. So let. Okay. Yeah. But okay. So let first delete. Okay. Well, I will go. See. So if n equal 2, L equals 0, ML equals 0, MS can be plus minus 1/2. So you understand that there are 2 electrons here because we can put 2, 0, 0, 1/2, and 2, 0, 0, minus 1, right? You understand this one. So this will be 2s2, right?
Yes.
If L equal 1, then ML can be 0, all right? Yeah. Sorry. Yeah, so L can be 0, N can be plus 1, and L can be minus 1. So for each one of them, MS can take 2 values.
Which makes it 6, okay.
Yeah. So the total you can put here is 2p6, right? But in our case, we have an atom that has 7 electrons. So we already put 1s2, 2s2. So the remaining, we can only put 3 for this, because this atom has 7 electrons, right? But in maximum, you can put up to 6. Is this clear? Can you hear me? Can you hear me?
Yes.
Yeah, well, for some reasons, honestly, the network, even I'm here and the network is cutting, so that's why if it breaks, well, send me a chat or something like that. Okay. but okay. So let's go to let's go to what I. Okay, so now let's talk about the degeneracy again. So what is the degeneracy? The degeneracy is the number of state or wave functions or possibilities of the wave functions that can change without changing the energy of the shell or the subshell, energy of the shell in general. So let's talk about n equal 1. We start from n equal 1, which is shell k. Okay, n equal 1, ml can be 0, ml can be 0. Okay, now if you limit yourself to this only, there is only one wave function here, which is 1, 0, 0. There is only one electron. So here the degeneracy is 1. The degeneracy is 1, which means the number of wave functions are 1. However, if you include the spin in consideration, now you have two possibilities. You have one that corresponds to plus 1/2, and you have another one that corresponds. I don't know why it doesn't work anymore. Okay, for some reason I cannot delete. So if I now if I include into account the spin, then I will have n equal 1, l equal 0, ml equal 0, and ms equal plus 1. And again, n equal 1, l equal 0, ml equal 0, another wave function that is minus 1. But both of them, they have the same energy. En is equal minus 13.6 n squared. So basically, if I give you the energy of this state, you cannot differentiate which wave function is giving me this. Is it this one or is this one? So this means that the degeneracy is 2. So there are two wave functions that can give you the same degeneracy, the same energy. Is this clear?
Yes, but doctor, I have a question.
Yeah.
Yeah, for the top part, if you were to take only n, l, and ml, so it will be 1, 0, 0. Isn't that unique? So it is not degenerate?
No, okay, so the question could be, this is a good question. The question could be, okay, for n equal to, for a state n equal to, shell n equal to, give me the degeneracy with and without spin. By taking into account the spin, by not taking into account the spin. Let's do it. Let the first thing do, what is n equal to? It is shell L. N equal to means that L can be 1, okay, and L can be 2, right? So ML here, you are not, okay, what is the, what is the mistake here?
L should be 0, not 2.
Yeah, exactly. Good. You see that I'm tired. I have been in meetings. Okay, L equals 0, L equal 1. So ML can be 0, okay? And here ML can be plus 1, 0, minus 1. Now, if I am telling you without a spin, what is the degeneracy without spin? In fact, here I can see this state has an energy, or this shell has an energy minus 13.6 n squared. We are talking, of course, about the hydrogen atom. And this energy level will be given by this state, this state, this state, and this state. So there are 4 possibilities. And we cannot, it's impossible to differentiate which one will give you exactly minus 13.6. And all of them, they give you the same. So here, the degeneracy is 4. Did you understand this? Is this clear?
Yes.
Now, if I ask you and tell you, what is the degeneracy including the spin?
Multiply by 2.
Exactly, because for each one, so this one will have 2 possibilities, this one 2, this one 2, this one. So you to multiply by, it will be 8. Okay, so this means there are 8, well, wave functions that will give you exactly the same energy. Okay, any question? Okay, so I have another. What is this? So, okay, thank you. Now, let's go to, we understood the degeneracy.
Sir?
We did the table of elements. Yes, yes. Zaid?
So I have a quick question about, yes. So I have a quick question about degeneracy. Is the like finding the how much the degeneracy it has, is it based off of the ML or off of the MS?
It's based on how many possibilities. Yeah, so it's based
Okay.
on many possibilities. So, for example, if you don't take the spin into account, well, here there is only one possibility. There is only 2, 0, 0. Yeah, right? So there is only one possibility here. Okay. Okay.
Yes.
Any question? Now, another thing I wanted to, this is chapter 8, but it is related to this. Let me just, okay, yeah. Now, how to remove the degeneracy? This is a very good question. How to remove the degeneracy? Experimentally, how to remove, not completely, but to remove some of the degeneracy.
Maybe you have to define the momentum.
To remove the degeneracy, we apply a magnetic field, the Zeeman effect. Okay, you might be asked, what is the Zeeman effect? The Zeeman effect, if you remember, in chapter 3, when we talked about the spectral lines, we said, and I also explained them last week, the spectral line, which is lambda, this is what you observe, for example, and then if you apply a magnetic field, you start seeing some of them, they split, and this distance, the split, increases when you increase the magnetic field. Some of them, they even go to 5. So why is this? Okay, and I covered it last time, but let me explain it here. How to remove the degeneracy is by applying a magnetic field. So, in fact, when you when you apply a magnetic field, what happens is that the electron will become, well, actually the magnet will have a magnet dipole, and then the electron, this dipole, will acquire a magnetic energy, and this magnetic energy will be of the form, this is magnetic energy, is equal to a constant called the Bohr's magneton, the magnetic field value, the strength of the magnetic field, and ML. That's why it's called the magnetic quantum number. Okay. Now, mu b is just a value. It's equal to the charge of the electron, the absolute value, h bar, divided by 2 times the mass of the electron. This will be given. Now, what happens here? What happens? Let's do the following. I have n equal 1. Please follow this, because this is very important. And we did not have time to cover it in detail in class, but I'm covering it here in detail. N equal 1, L equals 0, ML equals 0, and MS equal plus minus 1/2. Well, you can easily see that MS will not be included for the moment, okay, for the energy. So this is N equal 1. N equal 2. Again, L equal 0, ML equal 0, okay, and MS again. And L can be also equal 1. ML can be plus 1, 0, minus 1, right? And MS also. But except that in this case, MS will not affect the energy. Now, what is the energy here? The energy is minus 13.6 divided by 1 square. So the energy here is minus 13.6 divided by 4. The energy here minus 13.6 divided by 4. Minus 13.6 divided by 4. Minus 13.6 divided by 4. Do you agree? Hello?
Yes.
No. Okay. So now, what will happen now here if I apply a magnetic field? So each one of them will have an addition of magnetic energy that is equal to ML mu B. Mu B is a constant. B is the magnetic field. I can give you 2 Tesla, 3 Tesla. And ML is the value of ML. Well, you can see that for this specific case, the energy will remain the same. which means the wavelength will remain the same in the spectral lines. The same thing here, plus ml mu b b, so it is equal to 0 because ml equals 0. So this energy will remain the same. However, this one, it will have ml is plus 1, so it will be added plus mu b b with a positive value. This one, because it has ml equals 0, so it stays the same. And this one, because ml is equal minus 1, it will be minus minus, so it will be minus mu b b. And this will explain to you why some of them, they do not change, and some of them, they split. This one is the one that will split. You can see it was minus 13.6 divided by 4, and then it added a positive value, magnetic energy, and it added a negative value, so there will be a split. And you can see that the split increases with the magnetic field, and that's why I said this split increases when you increase the magnetic field strength. Is this clear?
Professor, if you can please give
Sorry?
one more exercise on this. If you can please give one more exercise on this or recap on this question, the same one.
Let me see. Let me see. I think in the here in the problem in the exam that I will be given. Okay. So yeah, I think yeah. So let's go and give an example.
Sorry, I just have a quick question.
Yes.
Will we be asked to draw that graph of the splitting in the exam?
You mean the spectral lines?
Yes.
No. Look. Okay. So that's a good question. Let's give an example. A very quick example. Let's apply. By the way, I will. Okay. So here is the question. Calculate the energy of a 2 or a 3D subshell before and after applying a magnetic field, let's say a magnetic field of 2 Tesla. That's a very good question. Calculate the energy or the energy values of a 3D subshell before and after applying a magnetic field of 2 Tesla. We are talking about a 3D subshell. Please pay attention to the question. I'm not asking you about the whole shell tree. So what is the meaning of 3D? 3D means n equal 3 and L equal okay.
2, 1, 0.
Yeah. So L is equal to, right? I want to make it bigger because so this means n equal 3, L equal 2. Now what is ML? ML
From 2.
yeah, so is equal to plus 2, plus 1, 0, minus 1, minus 2. Okay, so I will open the chat because there are several people who are okay. Now you can easily see that. Well, before let's see. Yeah, before magnetic field, the energy is the same. The energy is equal. En is equal minus 13.6 divided by
9.
9. Okay, so let's say let's do it very quickly, calculated so that so 13.6 divided by 9. So the energy will be minus 1.511 minus 0.511 minus 1.511 minus 1.511 minus 1.11. Okay, this is before. Now after, we know that after there will be an energy that is equal to mu. I always prefer by starting start by ml. Okay, so it's ml and then a constant mu b and then the magnetic field, which is 2 Tesla. Okay, for this the ml is 2. Okay, magnetic field is 2, so this will be plus 4 mu b, and mu b is a value, it's a given. For here ml is 1 and b is 2, so it is 2 mu b, so plus 2 mu b, so minus 1.511 plus 2b. Here plus 0 because ml is equal to 0. Here minus 2 mu b. Here minus 4 mu b. Okay, is this clear? So that's, if you remember, originally we had one spectral line that corresponds to this energy of minus 1.511. But now we have a split to 5. Okay, and this split increases as a function of the magnetic field. Okay, so this just so this is a way to remove degeneracy. Yes, Zaid?
So I just wanted to ask quickly, is mu b a constant?
Yes, mu b is, mu b is a constant. It will be given in mu b is equal to the electron, the charge of the electron, absolute value, h bar, which is given, and then 2 times the mass
over
of the
2m.
electron.
Okay.
So mu b
Okay.
is a constant.
Thank you, sir.
Okay.
Yes.
Yes.
I just wanted to ask, when you want to calculate the number, like the degeneracy, okay, that number, right? Do you count, like if you want it for n3, do you count for n1, 2, 3, or just for n3, the degeneracy number?
No, it will be based on the question. For example, I can ask you, what is the degeneracy of a subshell 3D? So
okay.
So this is the subshell 3D, right? So the subshell 3D is this one. All right?
Okay.
So the degeneracy for this one is 1, 2, 3, 4, 5 times 2. If you include the spin, it is 10. Right?
Yes.
Yeah. So that could be the question.
Okay. But
now,
it could be, for example, like N2 and N3. We'll have to calculate them.
Yes.
Or
yes. I can give you what is the degeneracy of N2, N equal 2. Okay.
But like you will not ask about the previous numbers. So like if you give n equals 3, we don't have to do it for 2 and 1 as well. Yeah?
No. If I ask you what is the degeneracy of shell L, well, shell L is n equal 2. Yeah.
Okay.
Doctor, just one question.
Yes.
So from what I understand now, applying a magnetic field using this Zeeman effect, it will help us differentiate between each orbital, between each 2 electrons, but not each 2 electrons that are spinning oppositely.
Okay.
For example, here we can differentiate between 5, but not all 10 electrons.
Okay.
That's
So
no.
To answer your question, no. The spin will also, that's a good question, just because we are recording and I don't want people to say that I'm saying something wrong. No, in this specific course until now, we did not cover the spin, but in fact, so this is not included in the exam. But yes, to answer your question from the physics point of view, yes, there will be a magnetic energy due to the spin. There will be another split.
I see. So eventually we'll be able to observe 10
Yes.
10
yes.
lines. Okay.
Yeah, 10 or less.
But for the scope
some of them will not change. You will not. Yeah. Okay.
Thank you.
Yeah. So yes, from the physics point of view, yes, when you apply a magnetic field, the spin will also have a contribution, except that in our case, I did not include it in this course. We did not cover it, but yes, it will be. It will take. Yeah, you should take it into account if you are doing things right. But for the moment, we are only covering the blue part, the interaction of the magnetic angular momentum with the magnetic field. That's it. Okay. Yes. what is else? The last thing okay, so the last thing I wanted to mention, the probability and the normalization, this we will do in the exam, this one. Okay, so let's start this one. So this is what you would get in the exam, something similar. So you would get the table of radial functions and wave function, I mean spherical harmonics, and then you will get those tables, I mean those integral, general integrals that might be helpful, and you will get also this transmission. Now remember, though this is a transmission when the energy of the wave of the particle is bigger than the potential barrier, and this is when the opposite. I mean, you can easily get it from here. So this always must be positive. So, and this always must be positive. So in this case, E is smaller, and in this case, E is bigger. Except that here you have a hyperbolic sign, and here you have a sign, a normal sign. So let's go to using the 4 quantum numbers. Write down all possible set of quantum numbers for the 5D state of the hydrogen. Now, remember 5D, we are talking about 5D. What is 5?
N equals 5?
Yeah, so N equal 5 and L equal
2.
L equal 2. So if L equal 2, then I will write it here. M is equal to plus 2, plus 1, 0, minus 1, minus 2. All possible set of quantum numbers for the 5D state of the hydrogen atom. And then ms is equal plus minus 1/2. Now, what are the possible states? Now, this is the question. So it will be 5, okay, 2, and then we can start 2 plus 1/2, 5, 2, 2 minus 1/2, right? And then 5, 2, 1, 1/2, 5, 2, 1 minus 1/2, and 5, 2, 0, 1/2, 5, 2, 0 minus 1/2, and so on. Okay, are you following? Well, I can 5, 2 minus 1, 1/2, and this also minus 1/2, and then 5, 2, 5, 2 minus minus 2, 1/2, and then minus 1/2. Okay.
Professor, is it pointy brackets, right?
Sorry,
For the quantum numbers, the sets, it's pointy bracket on both ends, right?
4 points.
Or is
Yeah. Yeah, you have to write 4. That was your question, right?
Yeah, I think.
Yeah. Well, maybe I'm not. I didn't write it good, but anyway, this is N, this is L, ML, and this is MS, and so for each one of them is the same 3 first quantum number. They are only differing by plus 1/2, 1/2, and minus 1. Okay, so write down all possible states of quantum numbers for the 5D state of the hydrogen atom. What is the total degeneracy?
10.
10. So the total degeneracy, you can see that you have 10 possibilities, but the energy is the same. Of course, we are talking about hydrogen atom. So total degeneracy is 10. And here is the, no, well, wow, I was generous for this 20 question. 20 for this question? Which year was this? 2018. Okay. Okay. A hydrogen atom is in a 2p state. Okay. When we apply a magnetic field of 1.2 Tesla, the energy levels do not split. According to the table of wave function for the hydrogen atom, what is the wave function corresponding to this situation? Justify your answer. The hydrogen atom is in 2p state. What is 2p? N equal?
N equals 2, L equals 1.
L equal 1. And then when we apply a magnetic field, the energy levels do not split. What does this mean? I can't hear you.
ML is 0.
So this means, yes, This means ML is 0. Why? Because the energy, the magnetic energy is equal to ML mu B. If for L equal 1, it will be either ML equal +1, -1, or 0. For ML +1 or -1, the energy will split. So this means that the ML is equal 0, which is very good. So now ML is equal 0. Now, what does this mean? This means that the wave function, which is NLML, our wave function, is equal to RNL times YLML. So this means that our wave function is 2, 1, 0, which is R21 and then Y10. This is what we will be looking for. Okay. So according to the table of the wave function, what is the wave function corresponding to this situation? Let's look at R21. So R21 is this one. Okay, so it's R exponential minus R over 2A0. By the way, so let me just make it clear. I will put it K R exponential minus R over 2A0. With K is a constant. This is K is this constant. I just don't want to take it, to write it down. So this is K, okay? And this is R21 of R. And then we also want 10 of theta and phi. So Y10 is this one. Even with the glasses, I can't see. So it's 1/2 square root 3 pi cosine theta. So our wave function, remember the K here is a constant that I just take it. So the wave function, which is 210, is equal to K R exponential minus R over 2A0 times 1/2 3 over pi. No, wait.
Professor, this is a different. Yeah.
Okay, thank you. Yes. So the wave function here, 210, is equal to KR, remember, exponential minus R over 2A0 times 1/2, I think, pi over 3 cosine theta. This is the wave function. Prove that this wave function is normalized. Okay, prove that this wave function is normalized. Now, remember, the wave function, the normalization of the wave function is psi star, psi, d of the volume, because you are integrating over a volume, must be equal to 1. Okay, now let's do it here. I will just remove everything here because now we know. Okay. So if you remember, you have to integrate from 0 to infinity over r, and you have to integrate from 0 to pi over theta, and you have to integrate from 0 to 2 pi over phi. And you do psi star, psi, but then you have to do r squared sine theta, dr, d theta, d phi. And this must be equal to 1. Now, 0, okay, 0 pi, 0 2 pi. So what is psi star and psi? Well, we are lucky here because the wave function is a real wave function. So this will give me k squared times 4 pi over 3. This is a constant times r squared, right? Exponential minus r over a0, and then cosine square theta, sine theta, dr, d theta, d phi. Okay. Now let's separate the variables. So this gives me 0 to infinity. Of course, this is a constant. So it's k squared over 4 pi over 3. It's a constant. And then r squared exponential minus r a0 dr. And then the integral from 0 to pi cosine square theta sine theta d theta. And then from 0 to 2 pi d phi. Of course, this one is 2 pi. It's easy. So we get it here. So this one is 2 pi. So you multiply it here. And this one and this one, you are given the tables here. You are given this table. And you are also given this table and this table. So you can easily calculate the integral. I will not do it, but you can easily calculate the integral. And if you calculate the integral, then you have to find 1. So whatever you get here, you multiply it by this. Don't forget that this is a constant that we put at the beginning, and this must be equal to 1. Any question? One remark here is, if I give you a wave function that has, let's say, that has this kind of shape, for example, y, theta and phi has something blah 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 exponential I phi or I2 phi. Okay, if you, when you do the normalization condition, remember that this becomes negative exponential minus I2 theta, and this remains the same I2 theta, so they cancel each other. Because many students, they don't pay attention to this, and then at the end they give me a normalization constant that is equal to, I don't know, 2i, because they integrated, they did not consider this, and they had, for example, I4 theta, and they integrated from 0 to 2 pi, and at the end they got an I, because they integrate. Okay, so please don't forget that the wave function or the probability of the density function has a psi star and psi. So whatever you have here, it will have a complex conjugate and they will cancel. Okay.
Professor,
Yeah.
just if you can please just explain one more time, how do these exponential cancel out? I did not get the idea.
So let's assume I have in a wave function this one. Let's take this as a constant. When I ask you to calculate psi star psi, well, psi has something exponential I phi, right? So when you do star here, it becomes minus I phi, and psi is I phi. So minus I phi and I phi, it gives you 1, exponential of 0. So they cancel each other. It gives you 1, right?
Yep.
Okay. So Zaid, you wanted to ask?
Yes, sir. I have just a quick question because I actually missed this. But what is, you mentioned K is a constant. What is that value? What is that constant?
I know, constant, as I mentioned, I am lazy. I did not want to write this. Okay, I put this as
okay.
Yeah. I put this as a constant. I don't want to, I didn't write to want to write it, but in fact, actually I can't even. So the constant will be 1 over a0 square root of 3, 2 times a0 to the power of 3 and by half. Okay, I just put it as a constant. So then you have to, when you integrate, you just replace it, and yeah,
you just substitute
it. Okay,
thank you, sir.
you're welcome. The electron, okay, this is also very good. Please, we did not cover it in class, but it's a very easy concept. So the radial probability is given by this quantity, this quantity. So if you want to calculate the radial probability of an electron in the wave in an atom, you use this. What is this? This is just a so the radial probability is equal to r squared, r the radius or the coordinate, and r the coordinates, not the radius, the coordinate of the electron. R is the radial function. This one that we used, R2, I think we used R21, right? It was R21, yes. It was, in this case, it was R21. Okay, and R21, it is KR exponential minus R over 2A0. With the K, as I mentioned, is a constant. This is R. The electron radial probability is given by where R is the radial wave function. At what radius is the electron probability at a maximum? So we want to find the maximum of this probability. What do we have to do? How do you find the maximum of a wave function? Yeah, so how do you find the maxima? Yeah, so you derive and you put it as equal to 0. So to find the maxima, so you have to derive this function with respect to R. Yeah. So then what you have to do is we know that let's say you have to derive this with R. What is R here? Is a constant R cubed exponential minus R over 2A0. So you derive it. So we can do it very quickly. So K is a constant. And then you put it equal to 0, of course. You derive and put it, because you are talking about maxima or minima. This is where you have the tangent to the curve is equal to 0. You have seen this in math. Of course, here you have to derive by part. So it will be 3r squared exponential minus r over 2a0 minus r cubed over 2a0 exponential minus r over 2a0. Don't tell me how I did it, because this is something that I think you are able to do yourself. Of course, the exponential will not be equal to 0, so I take it out of the histogram of the equation. So K, I can also take R, so it's R squared exponential minus R A0, and then what I get here is 3, all right, minus 1 over 2A0 is equal to 0. Okay, all right, and yes. I think, yes, this is what we did, 3r squared. And then, yeah, the derivative, I think that is right. So if this is equal to 0, this means that this is equal to 0. This means 1 over 2, by the way, this is r here. There is an r here. So r over a0 is equal to 3, which means r is equal to 6a0. So the maximum probability is, right, 6a0. Maybe I did a mistake here, but anyway, this is how you do it. We did it very fast. Let me just see. So r squared, yeah, there is a mistake here. Who can tell me what is the mistake? Who can tell me what is the mistake? Yeah. There's a mistake here. That's why I told you I'm going very fast. The mistake here is this. That's
Squared?
Yeah, exactly, squared. Okay. So yes, here it's a squared. Okay. R squared, sorry. So let's remove everything. Okay. It's the derivative with respect to r of what? R squared and times everything squared. So K squared r squared exponential minus r over a0. The mistake that I did is I did not put the function squared. Okay, so now we can do it very quickly. So this will give me the derivative, so K squared and the derivative of r to the power of 4 minus r over 0, and then K squared, and then it will be 4r cubed exponential minus r a0 minus, okay, minus r over a0 exponential minus r over 0. Okay, right? And then you can see that I can put r cubed here, r cubed exponential minus r a0, right? And then, so r cubed, this goes, it gives me minus 4r over a0 is equal to 0. If this is equal to 0, this means that this one is equal to 0. And you can see if this equal to 0, 4 minus r over a0 is equal to 0. This means that r is equal 4 times a0. What is 4 times a0? We know that in the hydrogen atom is n squared a0, right? Which means n is equal to. And this is exactly what we have, because we are talking about the state 2p, which is n equal to. So that's why we got the maximum probability is n equal to. Okay. Any question? So this is how.
Can you repeat the last thing?
So
I'm sorry.
So I reached this, and I saw that r is equal to 4a0. This is the maximum probability of the presence of the electron. And we know that the radius of the hydrogen atom is equal to n squared, principal quantum number, a0. This means from this result that n is equal to. And in fact, yes, it's true, because what we are dealing with is 2p state, n equal to. Okay. So what are the possible transitions between a 3D state and 2p state described above? Okay, I think this you know. So let me see. Okay. In fact, okay. So this is something new in the course. You need to know it, because otherwise this question doesn't make sense. So this is part of the course. This is something you for the first time you see. So it is part of the example. So if I have transition from a state, so I'm not answering this question, I'm giving a very important addition to the course here. So the transition, if I have a transition from a state that has n LML to another state that has another LML, any different, so the transition can happen. Not all the transition can happen. So the transition can happen provided three conditions. That if delta n can be anything. Delta L must be plus minus 1. The difference between L here and L here must be plus minus 1. If it is 2, it's impossible. And delta ML can be 0 or plus minus 1. Let's give this example here. What are the possible transitions between a 3D state and 2P state? So this is how I would answer this question. What is a 3D? 3D n equal 3 and L equal 2, right? So for L equal 2, I have ML equal 0, ML equal plus 1, and ML plus 2, ML minus 1, and ML minus 2. This is the 3D state. What is the 2P state? 2P state mean n equal 2, L equal 1. So if L equal 1, this means ML equal 0, ML equal plus 1, and ML minus 1. So any transition from here to here must satisfy this. Well, for delta n, we don't care. It can be anything. Everything is allowed. However, now let's see one by one. This is how you should do. From this to this is plus 2. Minus 1, this gives you 1. So this is allowed. This is from here. I will mark the ones that are not allowed in red. So the one from here to here is not allowed because 2 minus 0 is 2. This violates this. The same thing here. From 2 to minus 1, it's 2 minus minus 1. This is 3. So this one is not allowed. Now let's go to the second one. From here, from plus 1. From plus 1 to plus 1. 1 minus 1 is 0. So this is allowed. From plus 1 to 0, this is allowed. From plus 1 to minus 1, it's plus 1 minus minus 1, it's plus 2. So this transition is not allowed. And again, from ML equals 0 to 1. So 0 minus 1 is minus 1. It's good. ML to ML 0, 0. So it's 0. It's good. From 0 to minus 1, 0 minus minus 1 is plus 1 is good. And so on. Okay?
Professor, I have a question.
Yes.
Let's say L was equal to 3 and L was equal to 1. There's no transition allowed even for ML?
Yes. Yes. So if...
So we don't continue?
Yeah. So if N equal... Yeah, that's a good question. Let's say N equal 3, L equal 1, and N equal 2, L equal 1, right? And ML and ML, right?
Yes.
No, there is no transition that can happen here. Because delta
L is equal to...
is 0, exactly, yes.
Okay.
Yeah. So they have to
Why
be...
is it impossible?
Sorry?
I was asking, why is it impossible for this case?
Well, this is the beauty of quantum mechanics. If you take the wave function, and you calculate the probability of transition from n equal to L equal 1 to n equal 3, L equal 1, the quantum mechanics gives you 0. Probability is 0. And in fact, yes, experimentally, there has not been in any observation of this kind of things. So it's purely quantum mechanics.
Thank you. I just meant, what condition does it violate out of the 3 conditions that we wrote here?
Which one? The one that Marlene mentioned?
Yeah. Yep. Which condition does it violate?
Yeah, because delta L is equal to 0. Here you have L equal 1, L equal 1. So L minus L is 0. Here, no, L minus L must be minus 1 or plus 1.
Oh, I see.
Okay.
Thank you.
Any questions?
Professor, the stuff that you just explained, they're also given, like we have to study them for the tests, right? For the exam.
No, I will give it to no, this condition I will give it. But you have to know how to answer this question. Which I
Okay.
yeah, but these conditions I will give you. No, don't worry. Okay, so I think I will stop here because this one we did together. Okay, this one we did together. This is exactly the one with the transmission when I mean this is the tunneling when the energy is less than a voltage. So I will stop here. I can take questions, and then if you have any questions, you can also send them by email.
Prof,
Yes.
one request, please. Can you please send this document that we just solved to us so we can review it together?
This one? This one?
Yes, please.
Yes, I can. But I will send you the I will send you the video. I will. So you know what? I think I will upload another exam. This one is. I mean, I can upload it. It's not a problem. But this one is already recorded. What I can do, I can upload another one. Okay. Let me first